See the screen?
Yes.
All right, great. So I was thinking that today we will discuss stack and questions related to stack, right? So basically I want so first of all I was looking at Java, and this is the implementation of stack in Java. Are you able to see the code, or let me increase the font? So this is stack class inside the Java library, right? So first of all, it extends vector, and vector can grow and shrink, and it is synchronizable. It is synchronized. So in that sense, and it is always pushing at the end and also popping from the end, right? So pop operation is actually remove element at length minus one. So length is the total number of elements in the array, right?
Right.
Okay. And while pushing, it also add the element. So add element actually adds the element. So it basically appends the element. So append the element at the end, right? And they have a peak. Peak actually does do not remove the element. It just return the top element, right? Like pop was removing the element, remove element at length. This peak is just returning the element at, right? Otherwise, if stack do not have any element, so if length is equal to 0, then it throws a empty stack exception, right? And obviously there is an isEmpty function. IsEmpty function returns true if the stack is empty. Then this is one extra function, which is search. So it allows searching also inside the stack. So it's a very small class. That's it. So it's end of the class, right? Other functions, of course, it is inheriting from vector class, right? So we want to implement similar thing. We want to implement similar thing, and we want to implement a stack using. So obviously there can be two implementations of stack. One is the linked list implementation, and one is the array implementation, right? So let us look at both of them. So let us look at the array implementation and the linked list implementation. So let us say this is array implementation, and this is linked list implementation. In the array implementation, we have an array. In the linked list implementation, we have a structure of node, right? So linked list implementation is fairly simple, that we will always insert at head. So push function will insert at head, and pop function will remove the first node and return the value of the first node, right? So it will just remove from head, remove the first node, remove from head, and it will remove the first node. So head is always pointing to the first node. So let us say if I say push 1, then let us say push 2, let us say push 5, and then we say pop. So push 1 means a node with value 1 is created and head is now pointing to this. Then push 2 means a node with the value 2 is created and now my head is pointing here, right? Similarly, push 5 means a node with the value 5 is created and my head is pointing to this value, right? And since we are inserting at head, so it will take constant time. So push function takes constant time, pop function also takes constant time, and is empty is also a very simple function. Is empty just checks whether head is equal to null or not, right? So if head is equal to null, then the stack is empty, otherwise the stack is not empty, right?
Right.
All right. Similarly, we can look at the array implementation. So array implementation has an array and a variable top So top actually points to the current top actually points to the top element of the stack, right? So initially top is -1, and this is a condition for empty. So is empty is like if top is -1, then so return top is equal to -1. So this is my is empty function, right? And we have one push and pop function. So the push function is fairly simple. Void push, it receives the data integer d, and top is pointing to the top element, so push actually insert at top plus 1, right? So a of plus plus top is equal to data. So plus plus top means 0, so top is now pointing to 0, and a of data is equal to this. So if I am inserting 1, then 1 will be inserted at this position, right? After that, if I am inserting 2, then 2 is inserted at this position, and my top is here. After that, if I want to insert 3, then top is first incremented and 3 is here. Similarly, if I want to insert 4, 4 is here, 5, 5 is here, 6, 6 is here. After that, top will be here, right? So we need to check the condition of full also in push if we are having the array implementation, right? So condition of full is that if top is equal to n minus 1. If top is equal to n minus 1, then array is full. So we can just return or throw an exception. So ideally we should be throwing an exception here that my stack is full. Otherwise, it is like this. Similarly, pop function, right? So pop function will return an integer value. So what is the value that is returned? The value at top will be returned, right? So a top, this is the value that will be returned, and after that we will decrement the top. So top minus minus, and we will just return this value, right? But before returning, we have to check whether an element exists in the array or not. So before this, we have to check for empty condition. So if is empty, if the stack is empty, then we will just throw an exception or we will just return, right? So all of these functions, if you look at this push function, this is also constant time function. If you look at this pop function, this is also constant time function, right? Is empty function is also a constant time function. So all the functions are constant time functions, right?
Right.
Great. Uh, so the question is that I have an array. I have an array. Let us say size of this array is 10, right? So n is equal to 10. This array is A. I want to implement two stacks in this array, right? S1 and S2. So what is a better way to implement two stacks? One, two, three, four, five, six, seven, 8, 9, 10. Yeah, Amitabh?
Kamal, I think maybe the first stack you start inserting from the beginning,
Mm-hmm.
and the second you start inserting from the end.
All right, all right. So basically, what you are saying is that we will, since we are saying, so we will be saying that so there will be functions like this: push. So push in one stack value 2, or push in stack number 2 value let us say 2, right? So the first thing gives us the stack number, and the second thing gives us the value. Similarly, we will be having pop from stack number 1 or pop from stack number 2, right? So let us say these are the syntaxes. So we will be maintaining two top pointers, top 1 and top 2, right? So top 1 will be here, and top 2 will be here. So eventually this empty space can be used by either the first stack or the second stack. So basically both of them are drawing toward each other.
Yes.
uh, you remember the memory model of C language program, right?
Yeah, stack goes down.
Right. So
Heap goes up.
this was code area, this is heap area, and rest of the area is shared by both stack and heap. So
Heap.
heap and stack were actually growing toward each other. So this is the same thing, right?
Yes.
So heap grows, let us say heap grows downward and stack grows upward. This is not fixed that whether the stack grows upward or downward, but the fact that both of them grows toward each other. And the
Yes.
size of code area and data area is fixed. So this size does not change and both of them grows toward each other. So in a way, it is the optimal utilization of the total memory, right?
Hmm.
So the whenever a push happens in the second stack, top is actually decremented, and whenever a push happens in the
Yes.
first stack, top is incremented. Uh, the condition for is empty for the second stack is that if top is equal to n, then the stack is empty. Here the condition of is empty is if top 1 is equal to -1, then the first
Minus.
stack is empty, right? So all those conditions will be different for both of them, right? So we can
Yes.
we can map these two conditions for each of the stack. The initial values of top 1 and top 2, then the condition of stack being full, condition of stack being empty. Condition of stack being full is basically if top 1 plus 1 is
Is
equal to top 2,
Top two.
then both of the stack is full. So there will never be a situation where one stack is full but the other stack is not full. Either both of them are full, there is no space to push, or
Yes.
there is a space for both of them, right? All right. So the next question that comes is that how will you synchronize this? So since there are two tops,
Mm-hmm.
right? So they should be synchronized. What if so how will you write? Let us write the push function for both of them. So this is push function for stack 1, right? So push function for stack 1 is that a of plus
Plus
top
plus top.
is equal to data, and push function for stack 2 is a of
Top
minus top 2,
top.
this was top 1, is equal to data, right? So here first plus top 1 happens, right? And before that
Okay.
there is a full condition, right? So full condition, and here also we check for full condition,
Okay.
right? So so let us just divide these steps, right? So let us say first we check for full condition. This is my step number 1. I am checking for full condition. Then second step is that I am doing plus top 1, and third step is that I am doing a of top 1 is equal to data, right?
Okay.
Right. Here the first step is that I am checking for full condition. So let us just change the color. So I am just checking for full condition of second stack, right?
Second step.
Then second step is that I am doing minus top 2, and third step is that we are doing a of top 2 is equal to data, right?
Yes.
So let us say the situation is like this. That I have this array, and top 1 is here and top 2 is here, right? So 1 2 3, and let us say 5 and 8, right? So there is only one room for one element, right?
Yes.
There is room for only one element. Let us say thread 1, inside thread 1 we are so inside thread 1 we are performing all the operations for stack 1, and inside thread 2 we are performing all the operations for stack 2, right?
Okay.
And how the context which is happening is that first it check for full condition, so full condition is false,
Yes.
right? Then it does a plus top 1, so top
Increment.
1 is now here, and
Now it
then
becomes full.
context switch happens. So this is the point where context switch happens, right? So now the control moves to thread 2, sorry, before,
So you insert
yeah,
yes.
so before incrementing top one, it has checked for full condition, the stack is not full, right? And then a context switch happens. Then a context switch happens, control moves to thread 2. Thread 2 will check for full condition, right?
Yes.
Thread 2 will check for full condition. Right now, this is the situation. So thread 2 will check for full condition. The full condition is false because T1 and T2 are at a gap of, there is a room between T1 and T2. So full condition will be false, right?
Yes.
Then let us say T2 minus minus happens. T2 minus minus happens means T2 will be here, right?
Yes.
And then let us say we are inserting value 10 in second stack and we are inserting value 20 in the first stack. So 10 will be inserted here and then this push operation will be complete, right?
Yes.
After that, let us say control moves to T1. So T1 has already checked for full condition. It will not check for full condition again, right? What is it? What is it that it will do? It will do plus plus top one. So now top one is also here,
Override the value.
and it will override the value, right? So how will you handle this particular situation?
This this ideally can be done using a mutex also if you keep this critical section inside inside a common mutex, because there are only two threads, so I guess a single mutex should do it.
Right, right, right.
Because if there are multiple stacks, then maybe we could have used the semaphore kind of thing. But since here there we have only two threads, so only one mutex should do it.
Right. So you guys want to take it as a homework, right?
Yeah, sure, come.
Just look at the implementation of the implementation of stack inside the language library, right? So obviously, they are not having this particular situation where they are implementing two stacks inside one array, but basically we have to see whether if the same stack variable is being used in two different threads, whether it will work fine or not. You understand the difference, right? You have some idea of Java? Amitabh?
Yes. Come on. Sorry, I did not answer.
No
Listen,
problem.
last thing that you said.
So basically, I'm saying, let us say I have a stack variable. I have a
Yes.
stack integer. So let us say, this is my program, and in this program, I have a stack integer variable. So let us write a separate class, right? So I have a stack integer variable. Let us say this is S, right? So this S is a stack.
Okay.
And there are two threads which are using the same stack as variable. So then the problem of synchronization will be there, right?
Yes.
So language library must have handled it, or it may not have handled it, right? Similarly in Java, right? So just have a look at the language library whether this particular situation is handled or not, right?
Okay. Because I think in C++ stack it's not ideally handled.
So in Java, a lot of things,
seen-
lot of things are left as it is without being synchronized, and some things are synchronized. So I think the vector implementation is synchronized.
but I need to check the C++
Yeah.
14 or 11 version. Maybe there it's synchronized.
Yeah. Right. So obviously, when things are synchronized, it comes with a drawback also that its implementation will be taking little more time, right? Because it will always be checking for all those conditions, and it will be putting the critical section code. All that thing will be there, right? So that's why there are some collections which are kept as non-synchronized, right? Which are not thread safe, and there are some
Yes.
other collections which are thread safe, right? It is not a bad decision or good decision. It is just that if we can check whether a particular collection is synchronized or not, right?
No.
All right.
So, Kamal, the homework would be to create a full thread safe stack.
Homework is this particular
Or
function, this particular yeah.
just critical section. Okay.
So homework is that you have to implement two stacks inside one array, and those two stacks should be thread safe,
Okay.
right? So the operations in these two stacks should be thread safe. So let us come to the next question. And since only two of you are there, so probably both of you can try. So next question is that I have a stack. So there are three operations that we have seen in the stack. One is push, one is pop, one is empty, and another operation may be that peek returns the element at top without actually popping it out, right? And all of these operations are constant time operations. All of them are constant time operations, right? So we want to introduce one more function, which is get minimum. Get minimum. So get minimum function returns the minimum element in the stack at any given time, right? So let us say if I do push 1, then push 10, then get minimum. So get minimum should give me 1, right? Then if I say push, so let us say push 5, so it should give 5. Then if I say push 1, then if I do a get minimum now, then I should be getting 1, right? So first I have pushed 5, so 5 is pushed in the stack. If I do a get minimum, then it should give me 5. Then I have done a push 10, so 10 is pushed. Now if I do a get minimum, it should give me 5. Then let us say I push 3, so 3 is pushed. Then if I do a get minimum now, then answer should be 3. Let us say now I am inserting 6, the answer should be 3 now. If I insert a 1, then answer should be 1 now, right? Is the question clear?
No.
All right. And all right, go ahead. How will you do it?
You would whenever you're pushing a value, let's say push 5 in first, that becomes your peak value, and then each time whenever you're pushing, you check with the peak another temp peak value against this variable that you're pushing in, the value that you're pushing in. Whichever is smaller, that becomes your temp peak, and you can push and you can keep on changing the numbers.
All right.
Because the peak will tell you the top, it's always in the top. And that could be a supposed value that's the smallest. And each time, if another number is smaller, then it just replace that.
All right, great. So let us say, in this particular situation, that value, let us say, I have kept a minimum variable. Minimum variable is 1 now, right? This is what you are saying, Ankur.
I'm saying when you, but right. Let's say you start off with 5. 5 is the min value at the moment.
So
and
when
then
this,
you
right. So if I start with 5, then minimum will be 5. So if I want to insert push, so if I want to push 10, then minimum will not change. Minimum will remain 5. So when I push 3, then because 3 is less than 5, so minimum will be 3. If I push 6, so minimum will remain 3. If I push 1, then minimum will be 1, right? This is what you are saying, right?
Yeah.
So what if I pop? Now let us say I pop. So if I pop, then this 1 will be removed. So how will you reset the minimum? How will you set the minimum to 3? So after we pop, then the minimum should now become equal to 3, right?
Right. Great.
So in this situation, we will be checking the entire array. We will be searching the entire array for the minimum element. So
Okay.
push is a constant time operation, right? Get minimum is also constant time operation, but we have increased the complexity of pop operation. Pop operation has become on the order of n time operation.
Yeah.
Maybe we can use another stack.
All right.
But
So
only thing is it will take extra space. That's all. But the pop operation might become a constant operation.
that is fine. So let's say we have used an extra stack. So what should be the values? Initially, when we inserted 5.
Initially, yeah. So we'll push 5 to the new stack because that's the minimum.
All right. So push 5 to the new stack. Then 10. So 10 will not be pushed, right?
Yes.
Then 3 comes. So 3 will be pushed.
Yes.
Because 3 is less than the top element. So 3 comes, 3 will be pushed because 3 is less than the top element. Then 6 comes, 6 will not be pushed. Then 1 comes and 1 will be pushed. 1 will be pushed. So now if I pop, so we will check whether the element being popped is equal to the minimum element. So if the element being popped is equal to the minimum element, then we will pop it from the main stack. So this is my main stack. This is my stack and this is my min stack. So we will pop it from the stack and then we will pop it from the min stack also, because this element no more exists in the original stack, right? So let's say this is my original stack, right? And get minimum will always return the it will be
top
like
from the minimum stack.
Yeah, so it will be like peak of S1, peak of minimum stack, right? So it will be like min stack dot peak. Sorry, it is not peep, it is peak. So minimum stack dot peak, right? So that will be get minimum function. So push operation is that if the value being pushed is less than the top element of the minimum stack, then push it in the minimum stack also, right?
Correct.
And pop operation is that if the value being popped is equal to the top element of the min stack, then pop the element from the min stack also, right? Remove the element from there also. So this looks like a correct implementation, that push operation is also taking on the order of 1 time, pop operation is also taking constant time, and get minimum is also taking constant time, right? All other operations will be taking constant time. Yeah, so this will work. Or maybe, if we are having a linked list implementation of the stack, then so in the linked list implementation of the stack, basically we have node structure like this. Struct node, it has one data and node pointer next, right? So we can add one more field in the structure, which is get next minimum, right? So node pointer next minimum, right? And maybe we can have it like this, right? So when 5 is pushed, the data is 5. So there are two pointers now. One is head pointer and one is minimum pointer. So 5 is pushed. Let us say this is the next and this is the next minimum. So next minimum is null, next is also null, right? And head is also pointing here and minimum is also pointing here, right? Then when 10 is pushed, so 10 node with value 10 will be inserted at the head, right? Next of 10 will be 5 and head will be pointing to 10, right? This is the normal push operation. Because 10 is not less than 5, so minimum remains at 5. Minimum will not change, right? Is it fine up to this point, Amita?
Yes, come.
All right. Then if we insert 3, if we push 3, so a new node with value 3 is created. Next of 3 will be 10 and head will be pointing to 3. This is the normal operation. We will check 3 with the
Yes.
element at minimum pointer. So 3 is less than 5. So, you know, minimum will be equal to 3 now. Minimum will be equal to 3 now. All right?
Okay.
Right.
Yes.
So now if we want to pop, then head pop means removing the first node, right? Pop means we will be removing this node. So if we remove this
Yes.
node, then head becomes equal to head arrow next, right? So head will point to this node, and minimum will become, if minimum is pointing to the top node, then if minimum is equal to head, then minimum will be equal to minimum arrow next minimum, right? So next minimum is obviously this node, so minimum will be pointing to this, right? Right? Right?
Yes, correct. Yes.
So if we insert 6, then node with the value 6 will be here, and it will be pointing to 3. Next minimum will be null, and head will be here. So minimum will not change, right? Minimum remains at 3. So if you want to pop now, then only head will change. Minimum will not change because minimum is not pointing to the head node. Head node is not the minimum node, right? Then if we insert 1, so now my next will be 6, my head will be here, and because 1 is less than the current minimum, which is 3, so minimum will also be here, and next minimum will be equal to 3, right? So this next minimum field is actually used to maneuver between the minimum element, and the next field is used to move between the nodes of the original stack, right?
Yes, great.
So here also the push, pop, and get minimum operation will be of the same complexity, right? All of them will be constant time, right? But I like this solution, but I like the previous solution personally, with this one, where we are having a separate stack, because here, if elements are inserted, let us say in reverse order, then we are only keeping those elements, we are only keeping duplicates of those elements which are actually minimum, right? So it is possible that the size of this minimum stack is just 1, right? Here, with each node, one extra field will go, right? One extra field will be there with each node, right? Right? So, in one of my interviews, I was asked this question, and I have no idea how to do it. So I came up with this solution. So that's why I gave this, right? So I came up with this solution during the interview, and that's why probably, right? So these two are solutions. All right. Should we move to the next one?
Hmm.
All right. So let us say that I have a mathematical expression a plus b into, let's say, c plus d, right? So this is a valid mathematical expression, right? Now if I put more brackets, right? If I put one more bracket, then also it is a valid mathematical expression, just that these brackets in blue colors are actually duplicate. They can be avoided, right? Right?
Right.
So, given a mathematical expression, let us say in the form of a string, I want to check whether there are duplicate parentheses in the expression or not. Or if possible, let us just remove those duplicate parentheses. You got the question. Good?
Yeah.
All right. So how can we check for duplicate parentheses?
Well, it's kind of like matching the parentheses, but in this case, the idea would be like matching and looking for a row parentheses in the expression. But in this case, you're trying to find the duplicates that are in the expression, right?
Right.
So you could for each parenthesis you meet, you push it, like the starting parenthesis, you push it till you meet the end parenthesis of the expression, and then you pop the opening parenthesis and close it. But for that reason, the duplicates would be a bit tricky.
Sorry, can you come again?
As in, one of the questions that I was asked was if you have a mathematical expression, if you have a parenthesis that an opening parenthesis and not a closing parenthesis, find that particular missing parenthesis value. So in this case, the way you do for that one is that you push all the opening parentheses, and as soon as you meet another parenthesis that's a closing parenthesis, you pop them and you remove them out of the stack.
Right.
In this case, okay, so in this, if we have two opening parentheses, one after the other, then you can identify that there's a possibility that there's a duplicate parenthesis.
Yeah.
Happening.
Yeah. So
and
probably,
Kamal, like given this expression will always be valid expression, right? We just need to find duplicate.
Yeah. So we just need to find and remove the duplicate parentheses.
Okay, so we don't need to check whether the expression is valid or not. Only it's assumed that the expression is valid. Only we have duplicate parentheses, right?
But let us say what Ankur is saying. Let us say that we have to check. So there are two types of questions. This is different question from what. So one question is whether the parentheses are whether the expression is correct or not, right? It is like a plus b and then into c plus d and open. So this is not a valid expression at all, right? This is an invalid expression, right? So checking for whether an expression is invalid, so it's a separate question, right? So let's take this question first. How will you check whether the expression is invalid or not? Then we'll come to the opening.
In this one, you push the opening parenthesis, and when you meet the closing, when your next expression is a closing parenthesis, you pop that opening parenthesis and remove them.
All right.
And then if you meet a closing parenthesis, you check your stack. If it's empty, that means that is a problem. And so that means there's a missing parenthesis. Then the expression is not correct.
Right.
So in this case, but this one will get solved that way.
So there are three things. So there are basically following actions. First action is when a opening bracket comes, parenthesis comes, we will just push that parenthesis inside the stack, right? So this is action number one.
Yes.
Action number one is against the opening parenthesis. If opening parenthesis comes, then we will just push that parenthesis inside the stack, right? We will not do anything else. If a closing bracket comes, then we will pop the bracket from the stack, right? So
yes.
we will pop a parenthesis from the stack and we will check whether the two are same or not, right? So it may be like a plus b into c plus d. So this is also invalid parenthesis, right? Because the opening bracket is actually a opening parenthesis, whereas the closing bracket is actually a closing, this curly brackets like code, right?
Right.
So what we can do is that whenever a closing bracket comes of any form, right? So this can be extended that we can have multiple types of brackets. So whenever a closing bracket comes of any form, we will check the top of stack. If the top of the stack is the opening bracket of the same form, exact same form, then we will pop it out.
Right.
we will pop it out.
Right.
Otherwise, it's a mismatch,
Right.
right? Then third action will be taken when the stack when my expression is over. So when I have finished the entire when I have finished processing the entire expression, then there should be nothing left inside the stack. My stack should be
Right.
empty now, right? So let us say if we have a situation like this, then first opening bracket comes. First opening bracket comes, so this opening bracket is pushed inside the stack. Then closing bracket comes, so this will be popped from the stack. Then opening bracket comes, so this will be pushed inside the stack. Then after some time, my entire expression is over. So when the expression is over, I will check the stack and I will see that corresponding to this opening bracket, I have not found a closing bracket. So it means
Yes.
the parentheses are not proper. The bracketization of the expression is not proper, right?
Right.
All right, great. Yeah. So now,
Very good.
similar logic can be extended for this, for duplicate parenthesis, right? In duplicate parenthesis, basically, we have to check whether uh, a pair exists, for opening bracket as well as for closing bracket, right? So this is duplicate.
Right.
So basically, what all are duplicate parentheses? One type of duplicate parenthesis is that if I am saying like this, a plus b, so this parenthesis is actually not required. Right. Another type of duplicate parenthesis is the way it is here, where I have put extra parenthesis around the same expression, which is not required. Right. So these three cases of duplicate parenthesis can be handled, um, can be handled separately. Right.
Right.
All right. Great. So I believe you can write the code for this. Right. Next thing is that stack is used in a lot of stack is used to simulate recursion also, right? So stack can be used to simulate recursion. Basically, what is recursion is that if I want to calculate a factorial of n integer fact of integer n, so basically we will say uh, sorry guys, I have to take this. Hello विष्णु, इंटरव्यू है, वो मॉक इंटरव्यू है 9 बजे से, उसको रिमाइंड कराने के लिए कॉल किया था। हाँ, बैंगलोर में। तो उसका मेल आई है शायद, वो तुम्हारे पास भी आई होगी मेल। उसमें मेल में उसने एजेंडा भेजा है, जो वो डिस्कस करना चाहता है। ठीक। हेलो।
Yeah.
या सॉरी गाइस, सो दिस वाज एन इम्पोर्टेंट कॉल, राइट? So basically fact is return n into fact of n minus 1, right? So if we are, and then there is a terminating condition that if n is equal to 1, then return 1. So inside the memory stack, how it will be done is that if we are calling it for fact 3 factorial of 3, then first activation record will have n is equal to 3, then second activation record will have n is equal to 2, third activation record will have n is equal to 1, then the function which have n is equal to 1 will return 1 to the function where it is 2. That function where n is equal to 2 will multiply the return value with n, so it will multiply 1 with 2 and it will return 2 to the function where n is equal to 3. Where n is equal to 3, that function will multiply n with this return value, so it will multiply 3 with 2 and it will return 6 to the calling function, right? So this in itself is a stack. So some situations demand to use recursion because they are very difficult to solve without recursion. So those questions can be done by using a stack if we do not want to use recursion, right? Amitabh?
Mm, Yeah, the last line I didn't understand. Like, we need to use stack not in case of recursion.
So basically, if we are using recursion, then
Yes.
in a way, inside the memory, we are using stack, right? Where activation
Yes.
record of each function is actually function is calling the other function, and something will be there in the activation record of the current function, right? So
Yes.
that is basically how recursion is implemented. So
Correct.
if we are not using recursion, if we are not using recursion,
Yes.
then the same thing can be done if we kind of simulate the recursion by using a stack at our own,
Okay. Okay.
right? So how it can be done for this particular factorial function is, I keep a stack and I will keep on pushing n inside the stack uh, as long as n is greater than 1, right? So we will push 3, then we will push 2, then we will push 1. After the pushing is done, then we will just pop from the stack and multiply the number, right? So first will be while n is not equal to 1, or while n is greater than equal to 1, s dot push n, right? So after this is done, then we will do integer factorial is equal to 1 while n while s dot is empty. So while my stack is not
Not
empty,
not it.
not empty, f is equal to f into s dot pop, right? So if you look at it, then this part, the first part, is actually the function calls, right? So basically, recursion has two parts. First, the functions are calling each other, then they are returning the values to the other function, right? So this part is actually the calling part, where we are pushing the values inside the stack, and this part is the returning part. So while returning, we are performing the multiplication. So while returning, 1 will be multiplied with the value of n, then this value will be multiplied with the value of n, then this value will be multiplied with the value of n, and finally the value will be returned, right? So we have kept f, and this value will be multiplied by pop value, whatever is there, right? Then this value will be multiplied by pop, and so on, right? So this is actually the first while loop is actually returning the function calls, and the second while loop is actually showing us the process of functions returning in the recursive model, right?
Yes.
Now this may not be a good example. A good example is probably if we are using uh, if we have a binary tree. Let us say that we have a binary tree a, b, c, d, e, f, and g, right? I have a binary tree like this. What is the pre-order traversal, or let us say what is the in-order traversal of the binary tree? In the in-order traversal, we first call the void in-order node pointer root. So in this in-order process, we first call the in-order of r arrow left, then we print the current root value, and then we call the in-order of r arrow right.
Right.
Right? We print the current value, cout r arrow data. Right? So now this function is very difficult to write in a non-recursive way, and now of course we have a terminating condition. So this function is very difficult to implement this function in a non-recursive way, right? But it is easier to implement this function if we use a stack. So we use a stack. Inside the stack, we first push the value a, because a is not equal to null, right? So a will be pushed, then its left child will be pushed, b will be pushed, then its left child will be pushed, d will be pushed, right? So after that we hit a null means we will be returning, right? We are moving to the left child, right? So we are pushing a, then we move to the left child of a, then we are pushing b, we are moving to the left child of b. Then we are pushing D and we are moving to the left child of D. Now we hit a null. When we hit a null, we kind of pop it from the stack and then we print the value, right? So D is printed and the right child of D will be pushed inside the stack. What is the right child of the D? Right child of the D is null, so nothing will be pushed in the stack. Then again B will be popped, so B will be printed and then the right child of B will be pushed inside the stack. So right child of B is E, so E is now pushed inside the stack. E is now pushed inside the stack. Then left child of E is null, right child of E is null. So then again we will pop E. So E will be popped and E will be printed, and right child of E will be right child of E will be now considered. But the right child is null. So it means processing of E is also done. Then we pop from the stack again. So pop means we are actually returning, right? So we pop from the stack again, we print A, and then we move to the right child of A, which is C. So again, C, then we insert C and insert the left child of C, then we pop F and we try to insert the right child of F, which is null, so nothing will happen. Then we pop C, we print C, and we insert the right child of C, which is G. So after popping out, we print the value and we push the right child, right? Okay. So here we will be using this stack, but we are actually not using recursion. And we are using the same logic as that of recursion, right? So we are using the flexibility of recursion, we are using the logic of recursion without actual use of recursion. Does it make sense?
Yes.
My God, it was such an energetic yes. All right.
This, I guess, we need to try it first.
Exactly. So basically, the idea is that we can use stack to simulate recursion, right? And whenever a function call is happening, we will push inside the stack. Whenever a function is returning, we will pop from the stack, right? So that way, it is easier to write a non-recursive function to do the in-order traversal, right? Otherwise, writing non-recursive function for in-order traversal may be very, very tricky, right?
No.
All right. All right. So last question of the day is that let us say I am given a string. This string has only A and B's. It has only two characters, A and B, and there is a third character C, which is appearing only once, right? So this string has A and B's and C, but C is appearing only once. So there are some A B's before C and there are some A B's before after C, right? So we have to check whether the string before C, whether the substring before C is actually in the reverse order of the substring after C or not, right? So if you look at it, then the substring is that B and this one is also B, right, from the reverse order, right? So the function should return true for this kind of arrangement. Otherwise, the function should return if the arrangement is like A, C, B, A. Then for this particular case, the function should return false because the characters before C are not in the reverse order of the characters after C. Right. Is the question clear?
Yeah.
All right.
Yep.
So it's a simple function, right? So it will return boolean is pattern, whatever the name of the function is, and it will receive one string. So how will you do it, Amitabh?
Yeah, we ideally will push all the elements into the stack until we encounter C.
All right.
And then once we encounter C, just pop the elements and check with the next character, next element in the character array.
B, B, A are pushed inside the stack. Then we found C. So after we found C, then
so we stop. We stop.
For each character,
we check.
For each character. So next character is A. So we will pop from the stack and see whether it is equal to A or not. It is equal. So let's move to the next character. Next character is B. So we will pop from the stack and see whether this B is equal to B or not. So this is also equal. Next character is also B. So they are also equal. So it means it means I should be returning true, right?
Yeah. And also, I guess maybe at the end we need to check, the stack also should be empty.
All right. So the stack
possible
should, right. So the stack will be empty when length of the substring before C is not equal to length of the substring after C. Is maybe less than the length of the substring after C, right?
Yeah, it's like, yes.
Right. So what will be the complexity of this code? How much time it will take?
To take order of n, because
order of n, and how much extra memory?
This is n by 2.
Order of n basically, right?
Because we don't know where C is actually. Yes, correct.
So
we assumed
order of n. See, it will be, we will be using n by 2 memory. So n by 2 is actually order of n.
Yeah, correct. 2 to the power n, yes.
So n by 2 is order of n, right? So you, I think you have given the solution just because we are doing stack right now. But
yes.
Is it that complex a problem? Isn't it a simple problem? Isn't it a simple problem that we take two variables? Let us say this is low, this is high, right? So we will check whether element at low is equal to element at high. Then we will increment low and decrement high. So right, and we'll continue it as long up to the point where low is equal to high. When low is equal to high, we check whether the current character is C or not, right? And one check which we can do before that is that the total number of characters in the string must be odd, right? So if there are X characters before C, X characters after C, then it will be 2X characters. So it has to be even, and there will be one C character. So the total number of characters in the string has to be odd, right? Right, Amitabh?
Yes.
Right. So this was a trick question.
Okay. Because we are in between stacks, so
yeah.
I was thinking the same direction.
I thought the same thing. I never had that idea before.
All right, great. So let's meet tomorrow, right? So tomorrow we'll be starting with greedy approach, right? We'll be doing greedy and backtracking probably tomorrow and day after tomorrow, right?
Okay.
Right, and after that we will be doing string matching algorithms, the KMP, Robin curve, and other algorithms, right?
Okay. Yeah.